Our topic is lifelong VAEGAN for inpainting of damaged image regions. The aim of our research is both simple and ambitious: to design a model that automatically restores damaged parts of images and continuously accumulates experience without losing what has already been learned. Why is it important to talk about inpainting at all? First, in satellite imagery, our algorithms face a seemingly trivial but critical problem every day, like clouds. If we don't remove these obstacles, analysts cannot reliably assess the state of forests, fields, or other infrastructure. Second, in digital humanities, restoration of archival photographs enable us to revive unique historical shots that would otherwise be lost forever. Third, in applied computer vision, for example in security, we often deal with partially covered or masked faces. Proper restoration of such fragments improves the accuracy of subsequent recognition. Traditional manual approaches mean weeks of meticulous work by specialists and high financial costs. Hence, the demand grows for automatic methods that restore image integrity quickly, cheaply, and most importantly, semantically consistently. Achieving fully automatic and semantically correct restoration is exactly the focus of our study. Let us briefly see how approaches to inpainting have evolved. Stage 1 involved differential methods such as pixel propagation. They copied neighboring pixel values along branches user lines. It's fine for small scratches, but with larger holes the model began to smear paint, destroying sense structure. Stage 2 brought exemplar-based techniques. The algorithm searched undamaged areas for similar patches and copied them into the mask. Results improved. Real textures were borrowed, yet global consistency issues arose. A brick pattern could suddenly flip, perspective could break. Stage 3 welcomed deep networks, context encoders, GAN and VAE. They learned not merely to paste textures but to understand scene context and recreate objects realistically. However, classical GANs were trained for each domain separately and forgot earlier knowledge when moving to a new one. We now turn to the main challenge: lifelong learning that is continuous training without breaks. Imagine we first train the network on celebrity portraits and then at the architectural facade dataset. A classical neural network adapts quickly to new facades, yet starts to forget faces. This phenomenon called catastrophic forgetting. To prevent this, we merge two things: VAE, which models the latent space well, and GAN, responsible for photorealism. In lifelong VAEGAN, they share the same latent space, so new knowledge is inserted neatly beside the old, instead of pushing it out. Thus, lifelong VAEGAN does what humans do naturally. It learns all its life and doesn't forget what has already been mastered. Let us look at the core architecture of lifelong VAEGAN. It consists of 4K models. Inference encoder, it receives a damaged image and its mask and encodes them into a latent vector Z. Here the network forms an idea of what is missing. Generator, it takes that and reconstructs a complete image as if no hole ever existed. Discriminator compares real and generated frames, learning to tell them apart. Thanks to this context, the generator becomes ever more photorealistic. Generative replay, the key element for continuous learning. While training on a new domain, the network simultaneously produces its own samples from the stored latent space of previous tags and mixes them into the current mini-batch. This synthetic reminder prevents forgetting without storing huge datasets. All this runs in two phases. In wake, we update the net on real data via WGNGP. In dreaming, the net sleeps and using generative replay produces samples itself, minimizing a VAE-like elbow. Thanks to this wake-sleep cycle, lifelong VAEGAN steadily accumulates experience without sacrificing what it has already learned. This slide shows four principal improvements in lifelong VAEGAN. First, the dual-encoder. This uses the classical inference encoder with a U-net encoder. The first gives compact-let encoding, the second multi-level special features, so the model both understands meaning and keeps fine details. Second, skip connections. They pass feature maps directly from encoder to matching decoder layers. Sync contours and textures therefore survive the restoration, and the output is no longer blurred. Third, self-attention. In the bottleneck, each pixel can see the context of the whole scene, removing global artifacts such as stretched facades or grooved faces. To reinforce these changes, we add a perceptual loss. We compare generated and ground truth images in the feature space of pre-trained VGG network. This aligns high-level structure and visibly removes checkerboard and colors artifacts that plain MSE misses. At this stage, we abandon classic generative replay in favor of a buffer of earlier samplers. In the top images during the play, the bottom with buffer. After finishing each domain, we store a small representative subset of real images with masks. During training on new data, mini batches are randomly mixed with items from this buffer. So why is a buffer better for inpainting? First, it gives real local context, textures, lighting, perspective. Generative replay can miss such nuances. Second, it is cheaper for GPU. We don't have to generate dozens of images every iteration, simple loading from memory suffices. Third, the diversity of examples in the buffer prevents distribution drift. So the model overfits leads to the new domain and better preserves prior skill. Before discussing results, let us clarify how we measure them. MSAS, the mean squared error, it computes the average squared difference between the restored and ground truth image for every pixel. PSNR converts the same error into decibels, making it easier to read. The higher the value, the less noise and artifacts, handy for quick models compression on one dataset. SSIM looks not at individual pixels but at structural similarity in local windows. It is sensitive to contrast and geometry distortions, so it aligns better with human perception of texture and edges. Finally, FID estimates perceptual distance. It passes images through a pre-trained inception network and compares deep feature statistics. The lower the FID, the closer the distribution of generated pictures to real ones. Thus, each metric views quality from a different edge. MSA and PSNR low levels errors, SSIM local structure, and FID global perception. Now to the experimental results. We first trained the network on celebrity portraits, but these results were after training our model in the next dataset, so memory wasn't lost. And we have a very good results. MSE 0.205, PSNR 25.65, SIM 0.914, and a very low fit 6.81. Next, without restarting, the model switched to the much smaller facade dataset. Despite data scarcity, it held solid quality. MSE 0.303, PSNR about 23.94, SSIM 0.864, while fit rose to 44.24, but this is expected for complex architectural geometry. Here we can see the result with base VAEGAN model. The model reproduces the hidden areas, but their quality is questionable. This slide shows two sets of examples, face from Celeba and facades. In the top row, original images, in the middle row, masked images, and in the bottom row, output of Lifelong VAEGAN. The model on portraits restores eyes, nose, mouth, even complex hair texture seamlessly. On facades, we also have very good results. These samples were produced after switching from faces to facades, clearly proving Lifelong VAEGAN didn't forget faces while learning a new data type. First, the combination of a dual-encoder and self-attention was the main factor that sharply boosted detail and overall coherence of restored images. The model sees the whole scene while keeping fine textures. Second, a compact buffer of real samples effectively prevented catastrophic forgetting with negligible computational overhead. We keep memory without raising GPU demands. Our future work scale to more domains, adapt the network to Full HD images, and explore energy-efficient training. Thanks for your attention.